Hello, everyone. I counted in meantime. I think it's my fifth, or probably, I'm not sure, but I think it's fifth talk for Svitla. So long time relation. Today we'll touch. Yeah, last time if you had a chance, I think it was during vacation time. I had a session about the concurrent programming in Java, mostly focusing on the things that we have provided by the JDK, so things inside the Java util concurrent package. So we touched a lot of things around semaphores and logs and queues. Today, we will explore one specific thing that you can find in Java util concurrent atomic package. So there will be a lot of things around atomic variables. And we will explore one of interesting concurrent programming concepts. It's log-free programming. This is like, I have to warn you, this is really low level at some point. Just one slide with assembly, promise. But we will be talking a lot about CPU and how CPU works these days, and how it translates to your code to Java, and how Java uses some of these CPU constructs and instructions. And of course, it's all about speed and performance at the end of the day. So just to rephrase what Diana said, yes, I'm working in Neo4j for like 7 years. Yeah, I probably joined at the same time when the Smart Talk started. And I'm working in the same team for the last 7 years, optimizing performance of Neo4j database. And before Neo, I was doing a lot of things. I was doing like higher level things, building microservices and REST endpoints and all this lovely stuff and event-driven systems. But someday I decided, okay, what I really love is low-level stuff, JVM, and yeah, I found perfect place in Neo. So yeah, it's probably over 20 years with JVM right now. So let's go to the content. So I don't know how many of you heard the term log-free. So I think to make sure that we know what we are talking about, I need to like explain the concept. So the log-free comes from one of concepts in concurrent programming. It's called progress guarantees. So actually, if you are going to look and deep dive into log-free, you will at some point of time find this sentence that actually log-free is one of the properties of progress guarantees. So what are the progress guarantees? So basically, this is a set of properties of concurrent program that describe how many threads, processes, tasks is doing progress when executed concurrently. Okay, so we have a concurrent program that is composed of multiple tasks or threads, and progress guarantees basically tell how many of these processes, threads or tasks, you can use them interchangeably, units of work, how they progress, and how they advance your computation. Sometimes it's called liveness properties. So the weakest form, it's called obstruction freedom. So it means that out of your processes, tasks, and threads, only one thread is progressing, doing work, computing, mangling the bytes, moving things, and it's doing in isolation. So only one thread at a time is working, doing stuff. So this is probably the thing that you achieve using logs and things you achieve using synchronized in Java. And of course, the obstruction freedom, it means that there are no deadlocks in your code. The next level is log-free programming, so our topic for today. And what basically lock-free programming says is the system as a whole is making progress. So not the individual thread is making progress, but system as a whole is making progress. Okay, so maybe there are some things doing something, maybe some threads are progressing. There can be starvation. This is like side effect of lock-free programming, but some threads can not get enough time of CPU and will starve because they will be not scheduled for some reasons. We'll see it later. But basically, more than one thread is making progress, and the system as a whole is making progress. Okay. And then we have wait freedom, which is a really, I think, in my head still, after all these years, really complicated topic. And not many production level algorithms and data structures we can observe to have this property. So basically what freedom says, everyone making the system as a whole is making progress. So that's the same as lock-free, but we know how many steps is required to complete. So in a lock-free, you don't know how many steps there will be to complete your process, and the system as a whole is making progress. And in wait freedom, everyone is making progress, but you also know how many steps are required to finish. Yeah, I think it's a good question, and I will tend to respond to the questions right away because it will help you understand. The question from Roberto: lock-free applies just to one CPU or also can be viewed in cloud computing? Yes. So basically, the same concepts in concurrent programming apply to the things in distributed systems. So you will see some things that you can say, okay, what actually happens in my distributed systems uh, with microservices. And I have one example that will prove that actually you do lock-free. Uh, not only like you don't know that you do lock-free programming and then you do it every day and you don't know about it. And it's distributed. So yeah, it applies, the concept applies to distributed systems as well. So what is it? I think I like very this description, but in log-free programming, it doesn't mean you don't have logs. What it means is there is no way you're like algorithmically looking at your algorithm, at your code, there is no way in log-free programming that your system can log during the operations, okay? It will always make progress, okay? So how it works? Basically, the whole thing is in this read, modify, write, and this simple concept is like the foundation of log-free. So you may ask you this question, is it thread safe? You know, this operation when you increment one single variable. And the valid question is, of course, it depends on your CPU architecture, but let's be even Intel, which has like the strongest guarantees from like the commercially available to everyone CPUs, this operation is not thread safe. Why? Because it's actually not one operation, it's three operations. You load the value of an I variable, then you increment the value, and then you store. So it means if you have multi-CPU, multi-core CPU systems, it means that one core can load the I value, the other core can load the I value at the same time. So they will see the same, for example, 0. Then the one thread will increment the value and write it back, and the second thread will increment the value and write it back and will not know that the other thread, you can even think about the other service, like CPUs are like, I tend to think now these days that our CPUs are like basically distributed systems on a chip. So it's not thread safe. Okay, this read, modify, write sequence of operations. So how we can make them thread safe? One thing is we can use heavy synchronization mechanism like locks and mutexes and semaphores and synchronize. But also, we can use something that is available at hardware level. So I don't want to say every, but I would say vast majority of CPUs, and for sure ARM, Intel, RISC-V, so everything that you probably have in your data centers, cloud, and on your desktop, provide hardware level for something called atomic operations. And they are implemented at the CPU level. What is important in this discussion is that these are atomic operations for operations on a single memory location. So there is no support for doing atomic operations for multiple addresses, multiple variables. Okay, there are some discussions, and there are like pretty old CPUs like the Motorola 680 processor, when there were like some attempts to provide atomic operations for multiple addresses, but now we have atomic operations. How it works? So basically, it means that when you do I++ and make it an atomic operation, you will see in a second how you can do it, the CPU guarantees that no other CPU will be able to modify. So this is like the finest, the smallest possible level lock. This is lock at the level of your CPU. Actually, it's the level at the level of lock at the level of cache line. Okay, so your memory loaded into your cache is, when you do atomic operation, is protected. No other core CPU can modify it, and this whole operation load, increment, and store will be seen by your code as a single atomic. You can like try to even use like transactional operation. Yeah, it's atomic. I think is better word, because transactionality has different properties. So one atomic operation. Okay, let me check one thing, because I think I kind of lost one slide. Okay. So what kind of atomic operations you have? So basically, you can think like this increment can be atomic operation. Then there is a bunch of operations like exchange. So basically, you want to write the new value, but as a response, as a return value, you want to get the old. As you can see, these are three operations, and you can do it in atomic way. So there is atomic exchange. So write the new value, return me the old one. So, and make sure that nobody in the middle replaces the old value. Then you can do what I showed you, the atomic increment. And the most interesting for us is atomic concurrent swap. So basically, this sequence is like, if the current value is equal the expected value, then the current value will be equal the new value. So you basically do exchange, but under condition that the current value is equal expected value. Okay, so this is compare exchange. You do it atomically, and it's supported by CPUs. How it's done in Java? So in Java, there's this lovely package, Java with concurrent atomic. And the problem is with Java, and one of the selling points of Java is, you don't care about your hardware, because we take care for you about it. So in Java, it's implemented as an intrinsics. So basically, for every platform, ARM, RISC, Intel, PowerPC, Spark, there is a specific assembly code emitted, generated whenever you do atomic operation. The Java will go and see, okay, I'm on Intel, so I will execute this piece of assembly to do the atomic operation. You see the Java method, but actually underneath it's the assembly. And as you can see, this is from for Intel. Intel requires to prefix your operation with the word log. So it's like the log-free programming is a really bad name, because actually there are logs. But the thing is, they're like super low level. They even don't talk to operating system, as you can see. Okay, so this is like theory. Why we should care about this fancy thing at your CPU level. As you probably noticed, I work in the benchmarking team, and recently my boss joked that I don't care about features, but I care about performance, and it's kind of true. So it is all about performance. This is a benchmark done on my laptop, so pretty old AMD Ryzen 7 with 8 cores. And what I'm trying to do in this benchmark, what I did is I have 4 threads reading the value and 4 threads doing atomic increment. Okay, so 4 threads reading, 4 threads doing atomic increment. And I implemented it in, if you want, I can show you later the code for this benchmark. So I do atomic operations, I use read-write log, and I use good old synchronized. And read-write log is from Java concurrent, and then I do something I should call plain access, so I don't do any atomic, I just do the regular E++. So as you can see, the higher is better because this is throughput. So we are in a range of, over 600 million operations per second when we do atomic. When we go to synchronized, so the oldest mutual exclusion mechanism in Java, we get into the range of 7 million operations. So this is not like few percents difference. This is serious difference in performance. So atomics are really, really, really fast. Okay, you will learn later that this is not all beautiful, and it's not always perfect word, but if you think about a low latency system, short response times, like log-free is something worth to explore. Of course, I like pictures. So as you can see, this is the atomic performance of atomic operation, throughput of atomic operations versus the log and synchronized in Java. How we use it, and this is where we go to the essence of log-free programming, because there is one fundamental way of doing things, and the rest is like fixing some problems that actually, yeah, I can share shortcut for this test, of course. That's the question in chat, and I can show you later this code. So this is the essence. What you do, let's imagine that we are trying to build a stack collection, data structure, using atomic operations. So you can do atomic operations on integers, on booleans, and of course you can do atomic operations on pointers, on references. I shouldn't use this in the same sentence, pointers and references. So how you do it? In Java, you would create your a reference, atomic reference, which wraps your value you want to do the atomic operations on. And then you keep the head of your stack, okay? So how you do it? Whenever you want to push something on the stack, you create a new node, okay? Because you need to wrap, we use linked stack, yeah? So we need to wrap the new value in the new node, and we need a field that points to the next field on the stack. How it works with the log-free programming. You take the current head, you see here. This is like, if you focus here, you will understand the rest of the presentation. You take the value of the current head, you try to install, okay, say, okay, now my next field on new head will point to the old head. And then you do compare and set atomic operation, saying if the other thread in the meantime didn't change the value of the old thread, set the value of the old thread to new thread. Okay, you see it. If some other thread did this and like he win and replace the old head, you restart the whole operation. Okay, so you say, okay, so I will fetch the new head. I will again try to point the new head to the old head because it has changed, and I will try to reinstall it again. So it's often called a CAS loop, compare and swap loop. So in log-free programming is you can think, and I think this is good way to think about it. It's like optimistic logging in databases. Okay, you don't log, you try to do something, and if somebody else in the meantime changed the value of your entity in database, you just retry it, yeah, and try to do this operation again. So this is why you can think about it as optimistic logging. And this is why what I said in the beginning is like similar in the distributed systems, where you try to do something. If somebody in the meantime didn't do anything, it's fine. You can progress. And that's the beauty, because somebody, if you imagine multiple threads doing this, somebody will make progress. Okay, somebody will install the new head and put the new value. The other thread will keep trying. And this is where the starvation comes in, because there may be situations that the threads, it's expected. Yeah, it's kind of expected because we have empty stack at the beginning. So this is why we start with the empty structure. And if we are the first one putting the node, we'll see, okay, this is my top of the stack. And this is the essence, yeah, of it. So maybe let's take a look at a little bit more complicated example, and we'll take a look at the can we perform atomic operations on GPUs and TPUs? I would say yes, but not yet in Java. So there are like projects like Tornado VM, Tornado VM, that is basically implementation of JVM on GPUs, where we can get support for such operations. At the moment, no, not in Java. So let's take a look at more complex example when we have queue, not a stack, but first in, first out queue. And how would you implement it using the log-free? So basically, we have a head of our queue from where we consume the values, and then we have tail when we put our values on the queue. Okay, and it's again linked list, very special, helping dummy node that doesn't like represent the value. And then we have few nodes already in the queue, and we have a tail that points to the last node and head that points to the first node. So here we attach, here we consume. So how it works? When we want to put a new node, first we create a new node, and we don't initialize any pointers. Same as with the stack example. In the next step, we say, okay, we need to say that now the last node will need to point to the new node. You see it? So we do first CAS operation. The first CAS operation is, okay, the last node in the queue is pointing to the new node. Okay, what we want to put on the queue. But we need to do another operation that we need to say, okay, now the tail needs to point to the new node, because if we don't update this reference, we will be still pointing to the wrong value. Okay, so there's like second CAS operation coming, which will then, okay, when we switch references from last node to new node, then we need to say, okay, now the tail will need to point to new node. So we can like preserve the order of things on the queue. As you can see, there are two CAS operations. Yeah, so they are not atomic, because what I said, the atomic operation is on single memory address, on single pointer, single variable. So how we deal with this situation that we need to execute two class operations, and they need to be somehow seen as atomic. And this is quite often used pattern in log-free programming when one thread is helping the other thread to make your data structure consistent. We'll see it in the code for a moment. So let's see. We have our node, we have our value, we have our reference to the next node. This is something that keeps our value and points reference to the next node. Then we have our dummy node, of course, and then we have head and tail of our queue, and they are both atomic references. So how the things putting the value on the queue works? Let's be with me for a moment. I know it's like really complicated, so I'll try my best to explain. So what we do first, this is really often like the essence. You take snapshot of your current state. So in log-free programming, you almost never operate on the direct values of your object because this is shared mutable state. Okay, so you don't do, it's final, but it's actually mutable. So you don't do operations on your field object fields until really last moment, and you always work on snapshot of your data. So what we do is, as you can see, this is the same pattern. We have a while loop, and we say, okay, the current tail, we get the current tail, then we get a node that is the last one. Okay, so the node which we want to connect with the new node that we just created here. And then we do first operation, try to connect the new node with the last node. Okay. And then what we try to do is advance the tail. Okay. So we say, okay, if it's succeeded, we install the new thing, then I will try to advance the tail. So this is like offer. But if you think about it, the other thread can come in and any random place in this code. We can have like second thread doing things here and second thread doing things here anywhere. So how the second thread is helping the first thread. So imagine we have a second thread that is trying to get something from the queue. Yeah. So what happens is we take the head, we take the tail, okay? We see what is our thing we want to get. Yeah, so good question from Jarosław. So we need a forecast of next node behavior. So this is like the essence, okay, here. So we take the value from the head, and then we try to check if the tail is pointing to the wrong value, and if it's pointing to the wrong value, we try to help the other thread and do compare and set. So here, taking things from the queue is helping the other thread to say, okay, you managed to install the next, but you didn't manage to update the tail. I will do it for you, okay? And as you can see, if we don't succeed, in both cases, what happens if we don't succeed? Okay, if we don't succeed, we retry. So we say, okay, we take the new value of the tail, we take the new value of the last node, because maybe somebody in the meantime replaced them, and I will take the new snapshot of my object, and then I will say, okay, if the tail is consistent, so the current tail points to the last node, then I can do my stuff. If not, I will try to advance the tail. Okay. The same with polling. So as you can see, both threads are cooperating, and everybody is making progress. Yeah, there is no synchronize, there is no lock. Some threads will be like repeating and retrying all the time, but at least one will make progress. So this is the pattern. when you look at the majority of log-free algorithms and books, you will see this pattern. In the beginning, you take the snapshot of memory of your state, actually, and you keep it in local variables. You don't work with the global state. Then you try to modify your data structure, and then you try to, using single instruction, you can think about it as like committing your changes. If in between the state didn't change, because you remember, you capture your state. So there is a way that you can compare my snapshot with the current value. So if my snapshot is the same as the current value, I'm okay, everything is fine, I can continue. If somebody in the meantime change your current value, you need to recheck the state, reload the state again, and try to apply the modification, okay? That's the essence. And this is like the proof that you are doing log-free, not thinking about doing it, because this is, I think, the best description. What log-free programming is like working with Git. Think about it. You check out the state of the repository, you do your local modifications, and then you do Git commit. Okay, I will respond to this question later. So you try to do Git commit. In somebody else from your team modified the code you are working on, you will have to rebase. Okay, so check the code again, check out the new version, and reapply your changes again, and then again try to commit. So basically, Git is log-free, okay, compared to other like things, systems, version control systems from the 90s. Git is log-free, and this whole pattern, check out, modify, and try to commit is basically the log-free programming. Okay. The question is, this algorithm should be very consistent with memory management. Okay, I need like a little bit more background what you mean by memory management, because it can be like two different things. So Jarosław, if you can write down what you mean by memory management, and I will move to the next. How we prove it? So basically, it's quite complex, and there's like a lot of things going on. And the more CPUs you have, the more cores you have, the more threads. It's really hard to prove it by just drawing stuff on the board and trying to come up with these things. So there is things called JC stress, Java concurrency stress, and this is a framework. I will not spend a lot of time about it, but this is a framework to test if your code is thread safe. And this framework is used internally by JVM developers to prove that the structures in JVM are thread safe. In essence, how JC stress works is running your code millions of times and trying to break things, okay? So it runs your algorithm, and every time it runs, it checks the state, and if it's consistent with your expectations, it's fine. If not, it retries many times, because this is probably the only way you can prove it. Because every CPU has different characteristic. Every CPU has different way of managing caches and consistency across cores. So you need to run JC stress. So how it works, like simple example, you write your JC stress test, and you write two methods. One method is trying to put something on the queue, and the other method, the other thread, they call it actors, but it has nothing to do with actor programming. So one method is trying to put something on the queue, and one method is trying to take something from the queue, and actually is trying to record what it found. Okay, it can be null value, or it can be one, or it can be whatever. Yeah. And JC stress is running this in circles from multiple times, different configurations, and JC stress is trying to put like one thread on one CPU, second thread on the other CPU. Sometimes it runs the both threads on the same CPU, so it's trying to test all the possible combinations. And once it runs your actors, it runs something called, I should call it like arbiter thread. And arbiter, what the arbiter is doing is saying, okay, this is what I should see. Okay, so you define your expectations. So if you have one thread producing value and two threads trying to consume the queue, what are your expectations? Your expectations are that one thread will get the value and the second one will not get the value. This is a valid. Yeah. The other valid expectation is nobody will get the value because your consumer thread will execute before the producer. So we'll not see the value. And this is also expected, but either you don't see the value at all, or you see only one thread sees the value. And the things that you don't want to see is that both threads will see the same value, because this is not how queues were working, okay? And JC Stress is trying to run it and break your system using this simple thing. So there are ways to prove your log-free algorithms. And of course, there are ways to test it and think about it. You may ask yourself, okay, if it's so fast, I bet this is probably many of you, this is the first time you heard this term, log-free programming. Why we are not using it like everywhere? Because like everything in computer science is double-edged sword. The thing is that it works in most cases, except few corner cases. And they are really, really touchy. The hardest thing in log-free programming is something called ABA problem, ABA problem, ABA, whatever you call it. So what it is, imagine that one thread took the value of your atomic variable, did modifications, okay, so it keeps the state, did modifications, but some other thread get in the middle, also like took the state, modified, replaced it with the same value, and then the other thread wakes up and says, oh, nothing happened because I still see this old value, okay? Because it can really happen that one thread takes a snapshot of memory, the other thread will do modification, but it will install the same value, like, take something on the queue and put the same thing on the queue. It may happen, but this thread will be so fast, bad luck, it will get more CPU time, and the other thread will get the value and put this back the same value, and then the other thread wakes up, says, oh, nothing has changed. I'm okay with putting my value because nothing has changed. And then you are basically screwed, yeah? Because you don't even notice that the value changed in between, okay? So this is like the picture to understand. We have this A and D. One thread takes and tries to put B, but in the meantime, the other thread replaced the B and is pointing to incorrect place. How you can work around it? So there are some workarounds. One thing is something called tagged state reference. So what you do, you basically version your nodes, okay? So together with your value and atomic variable, you keep another thing that's called sometimes tag, sometimes stamp. And every time you do atomic operation, you increment the version. So when you do atomic compare and exchange, you say, okay, make sure that not only the value is the same, but the version we see is the same, okay? That's one, and it's supported by Java. It's called atomic markable reference and atomic stamped reference. Another solution to this problem is to use intermediate nodes. So basically what you do, you have node A and node B in your linked list, but you have something in between, artificial node that doesn't change, okay? So every node is separated by artificial node that doesn't change. And because this node doesn't change, we can rely on this information that nothing has changed, because there is like something in the, you do compare and swap on intermediate nodes. Another solution is making your structure immutable. Of course, something that we don't have to care about, default reclamation, because we have GC. In languages without GC, log-free programming is much more complicated because you need to dereference memory, you need to free the memory, and it makes things complex. So at least in Java, this thing is solved by garbage collector. So last example, and we can go to summary. And I will show you how the thing with stamped references, tag references are used to solve the ABA problem. This is another paper. I think it's from 70s. It's funny because this is the title of this paper is Pragmatic Implementation of Non-Blocking List. Actually, I haven't ever in my life seen a practical implementation of this data structure. So it's not useful at all, but I use it as example because it is a quite good explanation how to avoid this ABA problem. This linked list is not practical, but the way they propose to handle the ABA problem with stacked references is interesting. So and they use the atomic markable reference. So how the atomic markable reference works. So you do concurrent set, but when you do concurrent set, you keep your expected reference and then your new reference, and also you keep the value of the tag, of the mark, actually. So you expect the mark to be true and the new mark also to be true. So how it works? If you want to install this value as your new reference, only if the expected reference and expected mark are equal, then you will set the new reference and new mark value. Okay? So this is like extra if, extra condition, extra predicate to do compare and swap. So how it looks in the Harris linked list. It's all the same, okay? You have node, it's like kind of repeatable pattern. You have value, you have atomic markable reference this time. The value of the mark is false, and value of the markable reference is either null or the next node. Okay, I will try to answer the questions at the end. So the essence of this linked list is, okay, whenever you want to put something in this list, you need to find the place first. You want to find the place where you want to add a new value, and then install this value in the meantime. How it works. Again, you see the pattern, you take the current state, because there is some dirty trick, because Java doesn't support returning multiple values. We cheat a little bit, and we basically wrap our marker into array. And again, the same pattern. We try as long as we can, and this function is something called window function. So this is a function to find the place where you want to do your operation in your linked list. So you advance through your list, and you're checking. As you can see, you take the next, and you are like taking the next node, and you are checking if the next node is equal what you expected. So you do compare. And you say, okay, if this is this condition is met, it means I found the place, the spot in your linked list where I want to put value. But something is happening here. We check this value. So what happens is we need to somehow help with the situation when you traverse the linked list, and in the meantime, somebody else did the delete. And to avoid this ABA problem that you deleted, and in the same thread, you actually added once again the same value, what we do is we don't when we do delete, we don't delete, we mark it as deleted, okay? So we say, okay, if this node is deleted, I'm traversing the linked list. And if this node is deleted, it means I can physically remove it and retry, okay? So you go back and you take the current state and go on. If the node is not deleted, you continue. If the node was deleted, you physically removing. So traversing, this is how it works. Traversing the node also removes things that were probably in the meantime removed by other threads. So this is our window function, but finds the spot. And then when we do, this is how deletion works. You first call your window function to find the node that you want to delete. And what you do is, okay, you set the value of this node. Hey, this node is deleted. Okay, you try to physically remove it, but maybe some other thread will jump in and remove it for you in the meantime. But so just in case, you mark it really fast operation, mark it deleted. If you are lucky, you will remove it. If not, some other thread that will do the window function on the linked list will remove it for you. I remember about your questions, so no worries. How it connects with the Java memory model? Of course, all of these operations need to satisfy the Java memory model expectations, okay? The rules of Java memory model. So whenever you do get on atomic variable, it has the same effect as doing read or volatile variable, okay? Whenever you do, whenever you do a set on atomic variable, it has the same effect as writing volatile variable. So in terms of memory model, the safe publication, other threads seeing your state, changes to the state, it follows the same rules, that happens before relation in Java memory model. And it's the same for concurrent set, but it has the same effect as writing and reading to volatile variable. So I guess I hope I answered the question. Whenever you do atomic get, you are sure you see the last value and all the CPUs will see the same last value because it has the same semantics as volatile from the Java memory model perspective. So as you can see, it's quite, to get it right, it's quite complicated because of this one single problem, the ABA problem. Is log-free always better? Okay. The thing is that not every problem can be made log-free. So not all your problems can be made log-free. Because as you can see, these are single memory, maybe two memory locations operations where you can like a little cheat a little bit using, one thread helping the other thread. But there is no way to do like massive sections like you do with synchronize when you can wrap the whole methods in synchronize and you are fine. Okay, it boils down to really small fine-grained operations that can be log-free. Okay, there are some performance implications and there are some interesting problems at hardware level. This is super. I found it like I think in the beginning of this year when I was like I said, okay, I need new presentation. I was exploring more this. I was like really fan of log-free for a lot of reasons. And I found this paper, the cost of atomic operations. And actually, if you like sit down and think about it, they are expensive. Because if you have a lot of threads trying to do concurrent swap, what happens is you have the effect of wasted work, okay? Because one thread will be advancing and the other threads will be consuming your CPU time trying to reapply the state changes. So under really high contention scenarios, when you have like, lot of threads competing over the same piece of code and accessing the same piece of code. It can be faster, and it will be faster if you do good old, synchronize, or maybe synchronize is slower. Don't use synchronize. Use logs, please. I recommend my previous presentation when I was discussing these differences. Uh, but yeah, for highly contented scenarios, especially where you have like a lot of long operations. Okay, so you wrap a long operations into mutually, you need to do mutual exclusion for long operations. Regular logs are better. Why? Because if you have like a millisecond operation, there is a high chance that threads will quickly wake up, the operation will quickly finish, you will go grab your state, modify, go. Okay. If you have like IO heavy things or like really compute intensive operations, it means that the longer your locked section is, there is a higher chance that other threads will starve and repeat and reapply, basically waste your CPU cycles. There is also the cost of coordination of these changes, because every atomic operation is a lock on the CPU level, and at the CPU level, it's not only a lock, but also you get into this world of messy protocol in CPUs where the other threads need to be notified, but actually the value you see, it's not the value you should see, because actually somebody else had modified this value. So it causes a lot of traffic between your CPUs, if you do it, and uh, it's like, this is the thing that I was like shocked that actually when you do atomic operations, it means you lose this ability of our CPUs for parallelism at the instruction level. So you have pipelines in CPUs, many instructions can be executed at the same time, but because if you do atomic, it means you cannot execute things at the same time on the same memory location, because you put the lock, so it destroys your parallelism at the CPU level because you use atomic operation. Okay, so it's not always dandy and beautiful. To summarize, if you want to, during your next, job interview, if somebody asks you about lock-free programming, use this example of Git, because Git is lock-free. Because it's so complex, I highly recommend to have fun with writing your own implementations just to feel how it works, but use existing implementations, because there are like various libraries. And even inside JDK, there are some things that are already lock-free. And of course, always write benchmarks. If you say, okay, maybe I will try to use lock-free programming because when I use logs, don't do this thing that you go straight to lock-free and then, disaster on production. It's better to write benchmark. The things that you can use is, of course, Agrona, Disruptor, and JC tools, Java concurrency tools. That is a collection of data structures implemented using lock-free programming. And of course, in JDK, concurrent hash map, a concurrent link queue, a link transfer queue. If you will go down to the documentation, they will say in most cases they are lock-free. So sometimes in really nasty situation, they need to fall back and say, okay, I'm going, heavy lock, and I go to the operating system and, I say, okay, do the footex, do the lock, unpark the thread, the old way. So these things like concurrent hash map or concurrent link, you can sometimes say, okay, I give up with, retrying, and I do the regular lock. Even if you think and look in the lock implementation, the reentrant lock, the reentrant lock does the CAS loop, compare and swap loop, and if it fails, then it goes to unparking the thread and all this, black magic behind. When to do lock-free? Of course, when you want to squeeze most of your CPU, if you are bored with your daily work and explore like new things. And when I was starting my adventure with lock-free, I learned a lot about how CPUs work. The messy protocol, cache lines, the fact that the CPUs communicate asynchronously between cores. It's like super interesting, and when latency numbers are really important for you. Yeah, but you want to do as much as you can under the condition that you don't have long-running jobs. And thank you. That's all I had for today. I will share the slides with Diana, and I will share the content of it. I mean, the examples and code. Will give you a link to GitHub, where you have both the JC stress and benchmarks. And thank you for like very interactive session.
Hello, everyone, again. I'm not sure if you can see me, but I think you can hear me anyway. So, yeah, do we have any other questions? We still have time, I guess, like around 20 minutes that we can spend for your questions. So, if you have any, I think there is one new question,
Yeah.
right?
What about the high load, high concurrency? Uh, hmm. It really, I hate this answer. It really depends, yeah. If you have small tasks and you don't do I/O during your like the thing that will kill you, you kill your performance is when you fetch the state, then you go to some nasty microservice, do networking, you do I/O, and then you try to reapply the state, then you will lose, and then the good old log is a way to go. One thing that works and is actually kind of used in Java is adaptive locking. When what you do is you try to do lock free for like 3-4 iterations, and if you fail, you say, okay, this is busy piece of code. I will, revert to locking, and I will do the good old, mutual exclusion. And this is implemented like in JVM, and this is like good scenario when you use both. So in a happy scenario, you have happy path, everything is fine, you do lock free. And then if things are like getting contented, then you revert and go to locking. That's that's like interesting thing to play. On what side did you find the initial information about lock-free in Java? Oh my God. So there is a lot of and ton of good information inside Java docs about atomics. So if you start with Java docs and start reading about atomic variables, that's really really interesting starting point. Then it's worth to read this book, Seven Concurrency Models, Seven Java Concurrency Models. No, not Java. It's seven concurrency models in 7 days, when they describe different approaches to concurrent programming. And I think these are the two things that are worth exploring. Uh, and there is pretty old book, Art of Concurrent Programming. The problem with this book is like it has the valid information, it's all true, but it's pretty hard to read. And it's like, massive 400 pages something. But there's whole chapter about it. And there is a free PDF from Linux kernel developers, uh, Art of High Performance Code. And this is free PDF. I can send you the link. And actually, the Linux kernel, as you can imagine, is packed with lock-free things to make your operating system faster. And they describe a lot of things in this free PDF about lock-free. And the truth is, whatever is true about lock-free in C and C++, especially C++, is true for Java. There is this guy, oh, I don't remember, Herb Sutter. Also, yes. So there's a guy here. He is a C++ specification lead, and he has brilliant 4-hour presentation on how atomics work and log-free programming works in C++. And because C++ and Java have the same memory model, they follow the same rules. That's like surprise. So everything you see C++ guys talking about log-free programming is true for Java. Of course, C++ 11 and later. Okay, so this is the moment when the Java and C++ model like got coherent, and I highly recommend this presentation from C++ people about log-free because it's like one-to-one, the same concept, the same ideas. Then sometimes even the methods and names are the same. Oh yeah, I can like do whole separate session about stream parallel because I had like really bad days this year with this. So this is yeah, it's like really dangerous in some cases. Yeah, I will send links to the materials to Diana so she will attach it to my presentation, or I even will put a section in my presentation with links to YouTube videos. Yeah. Can it be useful for enterprise development? I would say no. Yeah. If you mean good old, Spring, good old EJB, it is more for low level, low latency systems. And if you go, low latency, you try to avoid frameworks as much as you can. Yeah. So whenever I was in a situation when the company I was working with was going, full steam, low latency response times below like, X millisecond, then the next step was, okay, we need to find something that it's not Spring, that it's not, EJB, that it's not heavy. So if you go low latency, at some point of time, you will say goodbye to your, good old Spring, and then you will see the benefit of log-free. So yeah.